do these death-defying roller coasters give people the thrills they seek? Every coaster relies on the same few physics principles, and today we'll look at the physics behind Flight Deck of Great America. Work, defined as force done times distance traveled, is the amount of energy that is done to a system to bring about a change. In this case, the chain lift is doing work on the coaster against gravity to move the coaster car up the hill. The roller coaster gained potential energy as it increased in elevation. Note that potential energy is energy stored in an object based on its potential to move from a certain height. Since this point is the tallest in the entire roller coaster, it is the point of maximum potential energy, the total energy of the roller coaster, and can be calculated with the following equation. Potential energy equals mass times gravitational acceleration times height. We can approximate the mass as 4,500 kilograms and the height as 31 meters. Multiplied by 9.8, the potential energy is 1,367.1 kilojoules. This potential energy is enough to carry the roller coaster throughout the entire rest of the ride, through varying conversions between kinetic and potential energy. As long as no other part of this ride is taller than the first hill, no additional work is needed to move the car. This demonstrates the conservation of energy. In an ideal world without friction or drag, the maximum potential energy is equal to the total energy, kinetic and potential, at any other point in the ride. Newton's first law states that an object in motion will remain in its state of motion unless acted on by another force. It is also known as the law of inertia.
In the loop-de-loop, the car wants to continue traveling in a straight line tangent to the circle. The track pushes on the car perpendicular to the direction it wants to go. This causes the car to travel in a circle. Riders experience what is called the centrifugal effect during the loop, where they are pushed down into their seats.
At this point, the roller coaster car is not moving up or down. This means that the forces acting in the vertical direction balance each other. Thus, the net force is zero. The forces acting on the car are gravity and the force of the rail on the car, also known as the normal force.
We can calculate the force on the rail needed to hold up the car by setting the force of gravity equal to the force of the rail. Therefore, since the force of gravity equals mass times gravitational acceleration, the force on the rail equals 44,100 newtons.
Here, the roller coaster car speeds up as it goes down the hill. This speeding up, or acceleration, is due to gravity's pull. The speed of the car increases because potential energy is converted to kinetic energy. On Earth, the acceleration due to gravity is approximately 9.8 meters per second squared.
The beginning of the corkscrew is point A, with a velocity VA and mass m. The end of the corkscrew is point B, with a velocity VB and mass m. Points A and B can be compared using conservation of momentum.
Momentum is mass times velocity and is conserved in most situations. In this case, since the mass of the car doesn't change, assuming we have no friction or drag, the velocity must be the same at points A and B.
If we assume velocity at A is 15 meters per second, then we can substitute the values into the conservation of momentum equation and solve for VB to be 15 meters per second as well.
Thanks for riding!